Welcome to lecture 17. In this lecture, I will talk about ideal fluids. Recall that in lecture 15, we derived the hydrodynamic energy momentum tensor from a gradient expansion of the underlying system. We found that if we worked to lowest order in the gradient expansion, to 0th order in gradients, meaning no gradients at all, we found that there are two terms contributing to the energy momentum tensor T mu. One term was proportional to the metric tensor G mu, and the proportionality constant turned out to be the pressure P. And the second term was proportional to the combination U mu, U nu, where U mu was a 4 vector that was normalized to be time-like. And epsilon here was the energy density. In the last lecture, we said that if we consider a curved manifold, we have to replace the conservation laws by covariant conservation laws, such as the law that would be the energy and momentum conservation takes the form covariant derivative nabla mu acting on T mu nu is equal to 0. In this lecture, we want to investigate what this conservation law means physically. To get started, recall that the 4-vector U mu is a time-like eigenvector of T mu nu. To see this, take the projection of T mu nu with respect to U mu, where projection always means that we have the same index appearing in both of the quantities that we want to write. If you plug in the form of the energy momentum tensor, one term contains the metric tensor G mu nu times U mu, that's the term that was proportional to the pressure. And since the 4 vector together with the metric tensor always gives back the 4 vector, we have this term to be given by P times U nu upstairs. For the second term, we now have U mu appearing twice. We can plug out, or we can pull out the 4-vector U nu from both of these expressions, and we have the remainder in these brackets here. And I have noted that the combination U mu is nothing else but our -1. That's how the 4-vector U mu was normalized in the first place. And since we now have a -1 and P appearing twice in this bracket, the P here cancels, and we find that U mu T mu nu is equal to minus epsilon times U nu. As a consequence, we find that the energy density is the time-like eigenvalue of the energy momentum tensor T mu nu. To see this, just take the double contraction of the energy momentum tensor with U mu twice. So we can use this result here and contract once more with U nu downstairs. We contract it with U nu downstairs. We have minus epsilon U nu, and that is nothing else but epsilon because U mu is normalized to -1. So this says that the time-like eigenvalue of the energy momentum tensor is just the energy density epsilon. What this means is that we can always use U mu to project out to the time-like direction of any tensorable quantity. All the rest will be space-like parts. We can also write down a space-like projector, and we call this one delta. The space-like projector is composed of 2 parts. One is the metric tensor G mu nu, and the other one is the combination, the symmetric combination of U mu, which will have the time-like part. And the point of this projector is that the time-like parts here will exactly cancel the time-like entry of the metric tensor, such that only the space-like part will remain. It is maybe most straightforward to visualize this by going to the so-called local rest frame, where we take U mu to be simply the vector 1, 0. If we do this, then in the local rest frame, the combination U mu, U nu just goes over to a diagonal tensor that has a 1 in the 0, 0 entry and zeros everywhere else. And the projector delta mu nu is also a diagonal tensor or diagonal 4x4 matrix, which has a 0 in the first row and first column and has 1 along the diagonal. So you can now see that in the local rest frame, it's clear that this combination here is the time-like part. It only picks out the time-like parts of a 4x4 matrix, and the delta here will project onto the space-like part of the 4x4 matrix. So essentially, these two tensors are complementing each other. Back to our main story, where we wanted to investigate the covariant conservation law of the energy momentum tensor, which was equation 17.2. We can now use the 4-velocity u mu to project out the time-like part of this. So we take the contraction of now delta mu t mu with respect to u nu. Because there's a derivative acting on the energy momentum tensor, there are many terms that appear. I'll wipe them out here. So everything in bracket here comes from the covariant derivative of the energy momentum tensor t mu. So we have terms here where the derivative acts on epsilon plus p. We have terms where the derivative acts on u mu. We have terms where the derivative acts on u nu. And we have terms where the derivative acts on the pressure and on the metric tensor. The first thing to notice is that the derivative on the metric tensor is defined to be 0 if it's a covariant derivative. So we can just forget about this term, it's 0. Now the next thing to look at will be other parts of this equation. So first of all, there's a part here that is u nu nabla mu u nu. We can recognize this to be the derivative of a quadratic form. So we can write this as derivative of u nu upstairs over 2, because that's what gives us back this form here. Now use the fact that u nu is just minus 1. So we get the derivative of 1/2, which is just 0. And this means that this term here, which contains this derivative of u nu projected onto u nu, vanishes because it's just 0. Furthermore, note that we have one entry here where we have u mu nabla mu acting on p. And over here, we have a term that is minus u mu nabla mu acting on p. So these two terms just cancel. So we find that after taking out all the terms that are 0 or cancel and multiplying by -1, this equation up here just ends up in the following form here. It's an equation that we have u mu nabla mu acting on epsilon and epsilon plus p, where nabla mu acts on u mu. Just as a side comment, since I said that u mu projects onto the time-like part, this combination u mu nabla mu is the time-like covariant derivative. So this is sort of like a time derivative, but expressed such that it is always pointing in the time-like direction, even if we are on a curved manifold where the time-like direction is not trivial to find. So this equation that we just derived, the time-like part of nabla mu t mu is 0, is this equation here. Now let's try to figure out what the meaning of this equation is. It's easiest for us to first consider the flat space limit, where the covariant derivative nabla mu goes over to the regular derivative partial mu. So we find that the equation 17.12 just has this particular form here. And next, what we want to consider is the non-relativistic limit, where this 4 vector u mu is expressed in terms of 1 in the time-like direction and some velocity v in the space-like direction. We will take v to be very, very small because we want to consider small speeds, so non-relativistic speeds. If we do this, we find that we have to keep only a few terms. And if we do this, then this first term here has 2 entry points. It has the connection u mu partial mu on epsilon, where if mu is 0, this is just 1 times the time derivative of epsilon. This is this term here, plus the space-like part of u, which is just v, dotted in the gradient of epsilon, which is this term here. And then over here, we have the divergence of u mu, which just turns out to be giving us the divergence of the velocity v here. So this is the non-relativistic limit of this equation here. And the last step, what we're going to use is we're going to use another, if you want so, non-relativistic limit, namely the one where we say that the energy density, which contains the mass density, is much, much bigger than the pressure if we are in the non-relativistic system. And the reason for this is that the energy density contains the mass density. So via m, the relation E is mc squared, we find that in this case, the energy density is always much, much bigger than the pressure. And we can neglect the pressure in this combination epsilon plus p. So we find that in this second non-relativistic limit, the time lag part of our conservation equation turns out to be this equation here, time derivative of epsilon plus v dotted into the gradient of epsilon plus epsilon times the divergence of v is equal to 0. And this equation should be familiar to you, which is nothing else but the well-known continuity equation in non-relativistic continuum mechanics. We can ask ourselves, what about the other parts of the conservation equation that we did not talk about so far? We can again use the projector, this time the space-like projector delta, onto this conservation equation and figure out what this equation means. If we do so, we can find an equation where we can take the flat space and non-relativistic limits, as well as the limit where we take the energy density to be much, much bigger than the pressure. And if one does that, which will be part of the homework for this lecture, you can show that this equation here, the space-like part of the conservation equation, turns out to be this equation here, where we get energy density times time derivative of velocity plus energy density times the dotted gradient onto the velocity plus the gradient on the pressure is equal to 0. And this is something that you can recognize to be nothing else but the Euler equation of non-relativistic continuum mechanics. Okay, to summarize, we find that the physical meaning of this conservation law in flat and non-relativistic spacetimes is just the combination of the equation of continuity and the Euler equations that are familiar from non-relativistic continuum mechanics. So these are, if you want to, the equations of hydrodynamics. These relations come out from the conservation equation here only when we plug in the hydrodynamic form of the energy momentum tensor 17.1 that we got from our gradient expansion in the first place. If we don't take the non-relativistic limit or the flat space limit, then these conservation laws, together with the hydrodynamic form of the energy momentum tensors, are the generalizations of ideal fluid dynamics, so Euler equations plus continuity equation, to curved spacetimes and fully relativistic speeds. So these equations here are the equations of ideal fluid dynamics. If we do that, then the vector u mu is nothing else but the full velocity of a fluid, and epsilon p are the energy density and pressure of this fluid, where you can check back at our earlier derivation that the pressure has to be related to the energy density via this relation here, which is known as the equation of state. We call these equations the equations of ideal fluid dynamics because we neglected so-called non-ideal terms when we basically neglected gradient corrections for our expression of the energy momentum tensor. It is not very hard to include, let's say, first order gradient corrections to the energy momentum tensor, T mu nu. The resulting expression will then differ from 17.1 and have additional terms. And one can check that then the conservation equations nabla mu T mu nu is 0 for this energy momentum tensor that is corrected, provides the equations of Navier-Stokes for a fluid in curved spacetime. So that is how you sort of get non-ideal fluids in the process. And that concludes the present lecture.